Thank you very much for the invitation to give a talk here. And in general, great conditions here. It's really great place. Okay, so I'll talk about billiards and polygons. This is joint work with Giovanni Forni and Francisco Arana Herrera. I want to start off with, I'm not assuming people know what ergodic theory is. So what is ergodic theory to me? Okay, so to me, ergodic theory is an area of dynamical systems that thinks the right way to understand the dynamical system is by understanding the measures that are invariant under the dynamics. And I don't know, this might seem a little preposterous. I think it's pretty successful. So maybe one way of selling that this is a good perspective is to say sort of one early theorem in the field. So I want to build up to that with the definition of what ergodic means. So we start with a probability space. In this setting for this talk, all spaces will be sigma compact metric spaces with their Borel sigma algebra, and the measures will be Borel measures on those. And sometimes the metric spaces will actually be compact. Okay, and we have a flow on the space. So this is a real line's worth of functions from the space to itself that obey the natural composition law. The function that corresponds to time square root of 2 plus pi is the composition of the function that corresponds to the function at time square root of 2 and the function at pi. Okay, and so an ergodic probability measure preserving system, well, first I want it to preserve the measure. So if I measure the size of a set before I apply the dynamics or after I apply the dynamics, I get the same number out. And I want it to be indecomposable in the sense of the measure. So if I take a measurable subset of the space and I move it forward by the dynamics and it stays the same, then I want it to be basically the whole space, to be the whole space from the standpoint of the measure. Doesn't actually have to be the whole space, but what it misses has measure 0. Of course, there's the other possibility is that it could be none of the space, or none of the space from the standpoint of the measure, which means that it would have measure 0. So we want it or its complement to be the whole space if it remains invariant under the dynamics. So that's the definition of ergodic theory. It's sort of a mouthful. What's the point of this definition? Is it lets you do some things. So this theorem is the Kerckhoff ergodic theorem. And what does the Kerckhoff ergodic theorem say? It says that in this context, if I have an L1 function and I observe where a particle goes over time and average over that time, I'll converge to the integral of the function of the whole space with respect to this measure for almost every point. There could be points that don't have this property, but from the standpoint of the measure, they're negligible. Okay? So maybe you don't care about the measurable category, maybe you care about continuous functions, or if you're in a sigma compact metric space, you can care about continuous compactly supported functions. What this tells you is it tells you that there's a full measure set that works simultaneously for all continuous compactly supported functions. And why is that? It's just in this context, continuous compactly supported functions have a countable dense subset in the supremum norm. And this average on the left-hand side plays very nicely with supremum norm perturbations. Okay, so this is sort of, I take this theorem as motivating that the definition of ergodic is good. Maybe another point to bring up is that this theorem is really saying that the obvious necessary condition is sufficient. So what do I mean by this? If you are not ergodic, so there's some invariant set of intermediate measure, you could consider the characteristic function of that set of intermediate measure, and the left-hand side would either be 0 or 1 valued for almost every x, but the right-hand side value would be something other than 0 or 1. So this theorem is saying that the obvious necessary condition, that there's no sort of indecomposable parts of the measure, is actually sufficient. All right, so ergodicity, so this is one very basic important property in ergodic theory, ergodicity, but there's a bunch of properties, and this is called the ergodic hierarchy. And this is a very abridged version of the ergodic hierarchy. There could be a bunch of levels inserted in between the 4 I will state, and you should read this as the amount of randomness increases as we go downwards. We start with less randomness, and we go downwards to more randomness. So first, your ergodic, if for any 2 measurable sets, You look at the measure of their intersection at a given time, you move one forward by the dynamics, you leave one stuck, and you average over time and you converge to the expectation. Okay. Now, weak mixing says that usually the measure of the intersection is what you'd expect. So what you'd expect is if things are completely independent, so it's the measure of the intersection then would be the product of their measures. And weak mixing says that as you move forward by the dynamics, you get closer and closer to this usually, because you're allowing yourself this average here. People happy about that? Then there's mixing, where you just want to become increasingly independent. So you don't do an averaging over time, and you just ask that as you move forward by time, you get closer and closer to being independent. And then there's something very far along the hierarchy, which is called Bernoulli, which is isomorphic to a shift on a product system. So you have some kind of finite set, you have a measure on that finite set, you build a new system by considering the countably infinite Z's worth of products of that set with itself. You do the same thing for your measures, and you want your dynamics to completely forget every time you move. So you just shift over and it completely forgets the state it was in before. And that's sort of the furthest along in the ergodic hierarchy. So these are the four I'm singling out in the ergodic hierarchy. Okay. And this talk will all be about weak mixing today. We're going to talk about weak mixing. So I want to tell you it's an important property. And how will I try and convince you it's an important property? I'll give you a bunch of equivalent definitions that have different flavors. So to my mind, that's a way of seeing that a property is important if it means a lot of different things that don't seem to be immediately the same property. All right, so I want to give you the definition of weak mixing, and I'm going to give you, I think, 7 equivalent definitions. So you're weak mixing if one of them holds, or respectively if all of them holds. So the first thing is I could start with my ergodic system and I could ask, well, is its product with itself ergodic with respect to the product measure? Seems like a question you could ask. That's one definition you could take about weak mixing. Well, maybe I don't care about my original system. Maybe I want my product with a different system to be ergodic. Well, if your product with yourself is ergodic, that implies with anything else you're ergodic. Now, for the entirety of this talk, I'm sticking with probability measure preserving systems, not infinite ergodic. All right, so these I don't call of being different flavor. I think these kind of have similar flavor. It's about product ergodicity. So the next thing, it has sort of a spectral theory that you have no non-trivial eigenfunctions in L2. So first off, I should tell you what an who wants to see the definition of an eigenfunction? Okay. Okay. There are trivial eigenfunctions, and those are just constant functions. Those are eigenfunctions with eigenvalue 0, as I'll try to choose to name my eigenfunctions. Okay.
Just a small question. Does it act by precomposition? Or?
Yeah, let me just give the definition. Thank you. So we say a function, let's say h is an eigenfunction. And let's just stick to the L2 setting. If h composed with f to the t, so if there exists an alpha, which I'll call the eigenvalue, is equal to e to the 2 pi I alpha t h, and this equality is in L2. Did that answer your question? Thanks for the question. By the way, is that chalkboard pretty readable for everybody? Great. Okay, so another thing you could think is maybe you don't like continuous time. I'll be honest, I don't actually like continuous time all that well. I like discrete time. So maybe I want to not measure continuously. Maybe I want to take discrete steps, say by size 1 or by size square root of 2. And I want to ask whether that's ergodic as a discrete dynamical system. Okay. Well, you could take that as being the definition that you want, that for all discrete times other than the trivial time 0, what you get is ergodic as a Z system. You could also go back to the definition we used on the previous slide, which is pair correlation related, And you could ask, when I pushed forward my dynamics by time, whether the correlations converge to the product, converge to what would happen in independence on some sequence. There's some sequence where things decorrelate as you go to infinity. We'll call this a mixing sequence, motivated by the definition of mixing from the previous slide, or alternately from the standpoint of measure, everything's getting mixed up. Why not? Okay, just having one is equivalent to all of these properties above, or you could be greedy and you could say, I want one pretty rich sequence or subset of the reals with density 1, so that for any subsequence taken from it, this goes to the product of this goes to the expectation, what would happen in the independence case. Should I define what it means for a subset of the reals to have density 1? Okay, great. So this is saying that the exceptions to looking like you're mixing are very, very slim, and that's equivalent to there just being one. Right? So to my mind, this is at least 3 fairly different flavors of definitions. There's sort of product ergodicity or discrete time ergodicity. That's 1, 2, and 4. You have the spectral version, which is 3, and then 5 and 6 is about sort of failure of correlation. So sort of 3 different flavors, and they all are the same definition. So that's how I'm trying to sell you that weak mixing is an interesting property, and you're not wasting your time here for the next 47 minutes or so. Cool. Oh, wait, I want to tell you, so this is sort of background about ergodic theory. Now this talk is really about one dynamical or arguably 2 dynamical systems. And I want to tell you about that dynamical system. So I want to tell you about the billiard and a polygon. And what are the rules? So I take a point mass in a polygon. I travel in a straight line for as long as I can. And what stops me? What stops me is I hit a side. And when I hit a side, I obey the law of elastic collision. So the angle of incidence is equal to the angle of reflection. And I continue on with the same speed. And what happens when I hit a corner? I go home. I give up and I go home. But outside of hitting the corners, which is sort of a measure 0 event, everything is great. So it's an idea behind this talk and why I'm giving a slide talk rather than a chalk talk, that a picture is worth 1,000 words. And so maybe a bad animation is worth even more. So here's one of the systems. So I've hit my slide and I come back out. And that's the angle of incidence is equal to the angle of reflection. Okay. Everyone happy about the system? So let's give the setup a little bit. So this is a dynamical system on the unit tangent bundle to the polygon. So you take your polygon and you let yourself have a whole circle's width of direction. So you care about the point you start in the polygon, but also the direction you start in. And there's going to be a relation on the boundary of the polygon, which is this angle of incidence is equal to angle of reflection. Okay. So the polygon has a natural area on it. The circle has its Lebesgue length, both Lebesgue. And so this unit tangent bundle has a 3-dimensional volume on it, and the 3-dimensional volume descends to the quotient space, and I'll denote that M sub q, and this space is denoted X sub q, and I'll say the words unit tangent bundle to the polygon to talk about X sub q. Right? So that's where the dynamics is going to be taking place. And so this is a natural dynamical system. You expect that it has been studied a lot. And so what do we know about it? Actually, we don't know all that. So one thing we do know is that the topological entropy is 0. This is a result of Kerckhoff. And so for those who don't know what topological entropy is, it's some kind of notion of complexity. It has at most a countable number of families of periodic orbits. So periodic orbits in these polygons, they can be isolated, but they can also come in families. So if you think about maybe the first one that I would think about, which is the billiard and the square, I have this periodic trajectory that comes here and bounces back and forth. Okay, but I also have this guy too. I have uncountably many that sort of look the same. So you want to lump them together in families. And when you lump them into families, then you have only countably many families. Okay. There exists a billiard so that the flow is ergodic with respect to this measure. This is going to be one of the main points of the talk, a strengthening of this theorem 3. to weak mixing property from ergodicity. Okay. All right, so now I just want to, so this is saying we know some things. And the next thing I want to say is that our ignorance vastly outstrips our knowledge. And so, there's a lot of people here, and some of you might be looking for new areas to pursue. I recommend this because there's a lot of extremely natural questions. You can explain to your neighbors the type of thing you're investigating in, and it's widely open.
For one, we only assume that you're only working with the boundary which is flat. Because if, for example, you have cavity, then you have.
Yeah, this is straight line segments. These are not smooth C2 boundaries. Yeah. There are people care about billiards in a lot of different settings, and they often have very different flavors and very different flavors from this one. Did that answer your question?
Yeah.
Thanks for the question. Great question. Okay. So there's an obvious obstruction, and I'm going to dig down on this so-called obvious obstruction to ergodicity with respect to this three-dimensional volume in the next several slides. So there's this obvious obstruction. And what that obvious obstruction turns out to be is that if all of your angles are rational multiples of pi, you can't hope to be ergodic with respect to this volume measure on the unit tangent bundle. But it is completely unclear if the obvious obstruction is the only one. And don't worry, at this slide, you don't see this as an obvious obstruction. I've got more pictures coming to convince you that this is an obvious obstruction. Okay, so we don't know if the obvious obstruction is the only obstruction to ergodicity. This is sort of outrageous. We don't know if every polygon has a periodic orbit. And we do know this fact, though, if all angles are rational multiples of pi, the same kind of obvious obstruction, we know this, and we know actually quite a bit about them. They'll call such a polygon a rational polygon if all of its angles are rational multiples of pi. We also know that all triangles with angle at most 112.3 degrees have a periodic orbit, and this improved on some big work that Rich Schwartz did to get to 100 degrees. Okay, so we know a little bit about periodic orbits, but there's a whole lot we don't know. And this, I think, to many people is a very basic question, but you could ask an opposite extreme. Maybe there are polygons where everything is very far from being periodic, where in fact, if you take any point whose trajectory is defined for all time, it will be dense in the entire unit tangent bundle. That's ruled out by a periodic orbit because a periodic orbit can't hopefully do that. So maybe we know that can't happen. That property is called being minimal, and we actually don't know if there's a polygon where the flow is minimal. So I think 2 and 3 together sort of highlight the extent of our ignorance. There's just some very basic questions, and you can ask some very strong properties, and we don't know sort of if there's any that satisfies. Yes.
Sorry, this is silly, but if you have a rational polygon, are all orbits periodic? Like,
if you have a rational polygon, not all orbits are periodic. And we'll be getting into that in a little bit. In particular, if you think about this square, it turns out that the flow on this is very closely related to the flow on the torus. And so when your flow corresponds to rational angles, you'll be periodic. And when they're irrational angles, you won't be periodic. And in fact, you'll be equidistributing. Yes?
So I don't know if you said this, but for your first question, in the rational case, do you know in the rational case it's ergodic?
It cannot be. That's the so-called obvious obstruction. So this is saying once you remove the obvious obstruction, and I don't expect that to be too obvious now, but I hope in the next couple of slides we'll make that clear. Great questions. Yes?
What's so special about 112.3?
I think there's a scary angle coming up, which is 112.5 that the methods break down. And they just got as close as they had the patience to get. Did that answer? I haven't studied this question seriously, but okay. All right, so here.
So, all your polygons are convex or not? We use it on all.
It doesn't matter actually.
Doesn't matter.
Yeah, so long as all of the lines and the boundary are straight line segments. That's super important, tying what he's saying. Otherwise, it's just a completely different world, but this doesn't really see whether they're convex or not. Any other questions? Okay, so what is special about all angles being rational multiples of pi? So I'll first say in words what it is. So we're gonna, yeah, maybe actually I'll show the picture first. So it turns out that a really good idea is rather than reflecting your trajectory so that it changes direction, you should reflect the table so you get a different table and the direction stays the same direction. So if you identify this table to this table, I'll refer to the polygons as tables, and I apologize if that confuses anybody. But if you reflect this polygon to this polygon, what you'll see is the arrow comes out exactly where it would have here, if I was a better drawer, which I'm not. So the idea is you should reflect the table rather than the trajectory. So now if you consider the group of reflections about the sides, you want to translate the sides to all be through the origin. Otherwise, you'll get translations and you'll mess everything up. But if you translate them all to being through the origin, if all of your sides are rational multiples of pi, you'll get a finite group. Okay? And that group will constrain the angles your original billiard. This is a trick to better understand the billiard trajectory. And that will constrain the angles you take to a finite set. And you can't possibly probe the whole three-dimensional volume if you only take a finite set of angles. You could probe the entire table, but you couldn't probe the entire choice of circles worth of directions. So that's why the angles being rational multiples of pi is the so-called obvious obstruction to ergodicity. And so this will be a theme throughout the remainder of the talk. So the results will split into two parts. The irrational case, where you have at least one angle, in which case you need at least two, which are irrational multiples of pi, in which case we want to ask questions about the volume, three-dimensional volume on the unit tangent bundle, or the case where you're rational multiples of pi, where you'll be concerned with an area measure, which is just the area of the polygon across a finite set, counting measure on a finite set, which are the angles you can take. Okay, so that's a picture. So now I just want to show you that there's a finite number of reflections you can take. In this case, you can take 8 reflections, and here are just sort of all of the options. And I wanted to decorate a little bit, but not so much that it would become confusing, what the sort of reflections are. So this red side, if you reflect from it, you get this polygon here. And this blue side, if you reflect from it, you get this polygon here. And maybe these ones are easier to see. If you reflect from this side, you get this one, this side from this one, this side here, you get this one, and so forth. Does that make sense? And you can get 8 choices. Okay. And now I want to show you what the dynamics are. So this is the dynamics in the original table, where I'm changing the direction of my trajectory. And here's what I get for that trajectory when I'm instead reflecting the polygons. Happy about this. So the moral of the story, there's 2 morals of the story of these slides. One is don't reflect the trajectory, reflect the polygon. And the other is that if all your angles are rational multiples of pi, don't even hope to probe the whole unit tangent bundle, hope to prove the polygon across a finite set of sides. And this setting, the finite set would have cardinality 8, which would capture these different orientations and directions. Okay. Do you have a question?
I'll just say, if your polygon has a tiny little bump on one of the sides, which of the questions you're asking would transfer to?
Oh, I'm sorry. Let me see if I get what you're saying. So I don't care about the square. I care about this guy.
Yeah, so you probably put a tiny little bump. You've asked various questions about the dynamics. Which ones would have an answer that would somehow be continuous under that rule?
Basically none of them. I think in particular, the entropy would become positive the moment you dumped out. Thanks for the question. Any other questions? Okay, so what's going on here is this picture I've drawn is something called a translation surface. So what is a translation surface? It's a Riemann surface with charts where all the transition functions between our translations away from a finite number of points, which you allow cone angles of integer multiples of 2 pi. Okay, and a theme of this talk is that a picture is worth 1,000 words. So I've drawn you a picture of a translation surface, and the sides that are identified are going in. I've drawn you one of these charts, and when you go off one of these sides, you move by translation to the side of the same color. Let me mention that the triangle is not in this. Depending on the projector, orange is very hard to see from red. So the triangle just is to tell orange from red. It isn't really there. Everybody okay with this? And so when I go off the chart here, I'll come back here by translation. And when I go off here, I'll come back here. Everybody happy about that? Yes.
But presumably if you made the bump also in Akshay's questions, make the bump polygonal itself, then many of the questions should be the same or.
Oh, yeah, then you have similar behavior and you can add, yeah. Then you have similar qualitative behavior. In principle, it could change some things. So for example, this guy was a rational polygon, but there's many ways you could make the bump be irrational, you know, something like this. Maybe this is some irrational angle, and then you could hope for ergodicity with respect to the unit tangent bundle volume. Did that answer your question?
And we can prove that you get some relation between this version and the one without the bump, or things like this.
Maybe the qualitative behavior, I think, is fairly unclear. The long-term behavior, you can make precise statements about large sets of measures tracking points very closely if this bump is taking place in a very small area. Did that answer your question? Thanks. Thanks for the question. Okay. All right, so that's a translation surface. So now let's go back to the previous slide. So the unit tangent bundle to the polygon is going to be foliated by translation surfaces. So it turns out that this is also a translation surface. That shouldn't be that surprising. When I cross over from this chart, I end up on this chart and I move by translation, sort of what's going on. And in every direction, your motion will be trapped in a translation surface, which will be a rotated copy of this. And so we should ask all of our questions about ergodicity, and the one I really care about for this talk, which is weak mixing, for the area measure on this object, which is 8 copies of my original polygon. Okay. And so once again, in the irrational case, we care about the volume measure and weak mixing with respect to that. And in the rational case, we'll care about weak mixing with respect to the area measure on these invariant translation surfaces in the unit tangent bundle. Oh, there's a space of translation surfaces. This really won't, because of the interest of time, show up in this talk. Secretly, all of the results about billiards and polygons in this talk, the new ones that I will give, are about rational polygons. And the way those are studied is not isolated gems on their own as being in a space of translation surfaces. That's how they're studied. And so I want to just dedicate one slide to the fact that there's a space of translation surfaces, and there's a natural measure on it. So I draw you an octagon, a regular octagon, and I claim that this is a translation surface where you identify the parallel opposite sides. So this is identified to this is identified to this. Blue is identified to blue, red is identified to red. Okay. And I can move around in this space. So I just drew one method of perturbation, which is I imagine this side is a hinge. So I imagine the vertical sides on top are a hinge, and I hinge the two vertical sides together, keeping them parallel and of equal length, and I get another octagon, which gives you another perfectly good translation surface. Of course, you could do this trick to all of the sides. You could imagine one pair of parallel equal length sides are on elastic bands, and you could stretch those. And in this way, you could move around in the space of translation surfaces. And in this case, you'd see that you have 8 parameters, 4 times 2 parameters. Okay. So there's and you can put a natural measure on it in terms of just viewing it locally as looking like R8. So just to recap, translation surfaces in billiards, if my polygon is rational, then the unit tangent bundle is foliated by billiard flow invariant translation surfaces. I will use the notion S sub theta, meaning the invariant surface in direction theta for the remainder of the talk. Okay? And many translation surfaces don't arise in this way. This is sort of an interesting thing. You put your rational billiard into a space of translation surfaces, and then it is a small set in that space. It's a measure zero set in that space, and nevertheless, it helps you understand billiard in rational polygon. Okay. And I think I've said these things. Okay, any questions at this point? So I want to now state one of the two main theorems of today's talk. So Giovanni Forni and I showed that the product of billiard flows on rational polygons is typically as ergodic as it can be. So let's make this precise. So if we take a rational polygon Q, once again, the dynamics are going to be stuck in invariant surfaces, but I can pick one invariant surface, the one for theta, and I can pick a different one, the one for psi, and I can ask whether this diagonal flow on the product of these two surfaces, so in this four-dimensional space, is ergodic with respect to the natural four-dimensional measure on this, which is just the two-dimensional area plus the two-dimensional area. And there might be bad thetas and bad psis, but those are a measure zero set. So for almost every choice of pairs, theta and psi, the product flow will be ergodic. Yes?
Just understand, if you're looking at equilateral triangle, this is saying something about the length of periodic orbits being irrational with respect to each other most of the time, or something like that?
So most of these invariant surfaces will actually not have any periodic trajectories. That'll only be an accountable number of directions. So the typical direction won't really see the periodic trajectories, at least not directly.
Maybe look at it, or, oh, I see, gotcha.
Yeah, thanks for the question.
So that times theta is no rationality property, no.
This is a completely inexplicit full measure subset of the circle cross the circle. Did that answer your question?
If you have a rational billiard, then you have this surface, but which has some rationality property. And if you deform it, you lose those rationality property. No?
The direction changes, the surface is fixed and the direction changes.
Yes, thank you, Elo. Yeah. So the name of the game is I fixed my polygon. I'm claiming that it's rational. I fixed my polygon, and then this is fixed, completely fixed. And then what I want to do is I want to consider the circle worth of directions. I want to randomly select theta from here and independently randomly select psi from my circle. And then the claim is for almost every one of those choices, so almost every with respect to length, cross length, the resulting diagonal flow will be ergodic on the product of the invariant surfaces. Did that answer your question? And thanks, Alon. Thanks for the question.
Is this describing the ergodic decomposition of the flow on the product of the unit tangent bundles?
Yes. No. No. Maybe on the product of the flow, the flow on the product of the unit tangent bundles, but the ergodic properties on the flow on the unit tangent bundle itself is an older theorem of Kerckhoff, Masur, Smillie from the mid-80s, which hopefully will show up in 7 minutes or so. Did that answer your question? Good. Yeah, so maybe I should say this, because why not foreshadow? We already knew that if you only cared about flow in one invariant surface, that was almost surely ergodic, and that's a result of Kerckhoff, Masur, and Smillie. And I will state that result in a little bit. So the surprising thing is, so what's new is that it's the product of the flow with itself. And so this was derived from a corresponding result for translation surfaces where the completely analogous result is proven. And from this, via a Baire category argument, which hopefully I will describe at the end of my talk today, so taking this theorem as a black box via a Baire category argument, you get that there has to be a necessarily irrational polygon where the billiard flow is weakly mixing with respect to the volume. And this comes from applying a Baire category argument to one of the equivalent definitions of ergodicity, which is the product of the flow with itself. Any questions on these?
So that's an analog of Kerckhoff et al. For ergodicity and with irrational.
Yeah. But replace ergodicity with weak mixing. And the point of today's talk, if you take nothing else, weak mixing is cool. Okay, so you could ask, this is a little silly. I could see why someone thought this is a little silly. So I don't talk about weak mixing for translation surfaces, but I decide when to start saying the word weak mixing, you know? And you could ask, well, why didn't I talk about weak mixing in this setting? And the answer is because I would have proved a false theorem. And it was known to be false, you know, it's not any deep insight. So we did not show that for a translation surface, the flow in almost every direction is weakly mixing. Or similarly, for a billiard in a rational polygon, the flow in almost every invariant surface is weakly mixing with respect to the area on that invariant surface. We didn't prove this, and that's because this is false. And you can see why it's false in sort of this picture. So the idea should be that as I change directions, my eigenfunction will stay the same, which will measure how high up this I am. So imagine that this is 2 pi, and I just do I times e to the I times how high up you are. And that will be an eigenfunction for every direction except the horizontal direction. So the eigenfunction will be the same, but the eigenvalues will change depending on your angle. And it's just not hard to see that you wrap around 1 time the whole time. It doesn't matter where you transport down because you're at the same level and you wrap around again and again and again. And so this one eigenfunction will work for all but one direction. Okay, so this is sort of, there's no hope to be weak mixing in typical directions. And of course, you could just paint the top side maybe that's, the same exact issue is taking place more or less for the billiard and the square. It's not weakly mixing in almost every invariant surface. It's not weakly mixing in any. And the reason is basically for the same reason as in this picture. So we don't want to prove false theorems, so we use an alternate version of weak mixing. We do sort of a version where something similar to it, where you're allowed to switch parameters and then get the theorem that we care via Baire category. Okay. But of course, I have another collaborator in the list. And you could ask, well, what if I've been stressing rational polygons, so maybe I care about them. I do, in fact. And so what we end up doing is we classify the rational polygons where the billiard flow is weakly mixing in almost every invariant surface. So we say if you're in some class, you are, and if you're not in that class, you're not. And we once again derive it from a theorem about translation surfaces. So the following 4 conditions on translation surfaces are the same. And the big one to take away is that you're weak mixing in almost every direction with respect to the area on your translation surface. And that's equivalent to having some direction. And it's equivalent to being weak mixing in the typical direction from the standpoint of the Baire category theorem. And what's the main thing going on here? It's that the obstruction is an affine map to the circle. So in this picture, there's an affine map to the circle going on. In fact, only depends on one coordinate. It only depends on the vertical coordinate, and otherwise you just crush the other coordinate. Okay. And from this, we obtained the following theorem that classifies the rational polygons where the billiard flow is weakly mixing in the invariant surfaces. And it's when you unfold to a branch translation cover of the torus. So you do this trick I devoted 3 slides to, where you reflect the table instead of the trajectory, and you have something that looks like the torus, and it covers the torus, and in fact is a translation cover. Or there's another obstruction, which after rotation, all of its sides are horizontal or vertical. So you look not like this guy, but maybe like this guy. Something like this. All your sides are horizontal and vertical, but that's not good enough. you need at least one of your horizontals or your verticals to have all of their lengths, which are rational multiples of each other. So say all of your verticals will all be rationally related. And I guess this one's free of charge. So these are the obstructions and these are the only ones. And these are honest to goodness obstructions. If these happen, you're not weakly mixing in any of your invariant surfaces. Okay. All right. And I just want to show you the picture. So we can do sort of more souped up versions of this obvious obstruction here. You could imagine that you go up 2 times an amount and half that amount up here, and you could similarly get an affine map. And I'm drawing level sets in different colors. So here's one level set of the affine map, and this ugly green color will be another level set of this affine map. Okay. So that's sort of the obstruction from the standpoint of translation surfaces. So I now want to briefly describe how the second theorem of mine with Giovanni follows from the first, taking the first about the product of flows and surfaces as a black box, you get something about irrational polygons. Okay, and we'll follow this isn't new. This is a strategy that goes back at least to Kerckhoff, Masur, Smillie, though probably the community knew that before. So the billiard flow in rational polygons is as ergodic as it can be. So if you fix a rational polygon, then for almost every invariant surface, the flow is ergodic with respect to the natural area on that invariant surface. And so this is derived from an analogous result for translation surfaces. And from this, using a Baire category argument, they prove that there's a polygon that has to be irrational, which is ergodic with respect to the billiard flow on that polygon. Is ergodic with respect to the volume. So you have a result about things that can't possibly be ergodic with respect to volume, but from that you derive a result that one of these guys is ergodic with respect to volume. And so deriving the second theorem from the first follows the same kind of outline, and I just want to first tell you the steps, and then given time, I'll explain the steps in a little bit more detail. So first, just take this as on faith. There's a notion you can define of approximate ergodicity, and you can define it so that it's an open condition. Okay? Proving ergodicity for rational polygons gives approximate ergodicity for a dense set of irrational polygons. Okay? And similarly for products. I care about weak mixing, so that's a product. All right. And then ergodicity holds by asking for stronger and stronger notions of approximate ergodicity and then intersecting over those thresholds. Okay? So what you end up with is an intersection of open and dense conditions. And the Baire category tells you that the intersection of open and dense sets, countable number, is non-empty. And that's how the argument works. Okay? Since I still have 8 minutes, I want to show you, would people rather hear more questions or for me to show some of the details of this argument? Who wants more questions? Okay, I think details wins, sorry. Yeah, I'm happy to tell you the questions later. I'll leave them up. Okay, so I want a version of ergodicity that plays well with being made approximate. So here on this side, we have an equals 0. So I could just change this to a less than epsilon or less than 1 over n if I want a countable number. So I want a version of ergodicity that admits nice approximation. And here's going to be my version of ergodicity. And I just want to restrict to 1 Lipschitz functions because everything else is too complicated for me. So I want to consider 1 Lipschitz functions. I want for every single 1 Lipschitz function, for every single 1 Lipschitz function, I can find a sequence going to infinity. So if I average my dynamics up to this time, and then I subtract from the expectation with respect to the volume, I'm very close to 0 in the following sense. So this depended on my initial condition. So now I can average over my initial conditions, my x and theta, and I want this to go to 0 along this sequence. And it turns out that this is equivalent to ergodicity. this condition. And the approximate version is you just replace the equal zeros to a less than epsilon. And you ask for one time. You don't want a sequence that's too hard. You just want one time. Okay, that's approximate ergodicity. And it turns out that approximate ergodicity is an open condition. Okay. So now I want to complete the argument via the Baire category theorem. And I claim that the ergodicity result of Kerckhoff, Masur, Smillie gives me that for each fixed epsilon, the set of polygons applying, having approximate ergodicity at threshold epsilon is a dense set. I already know it's an open set. So yes.
Approximate ergodicity involves a specific choice of F or a quantification over F?
So one-Lipschitz functions are a compact set in supremum norm. So it doesn't matter if you ask one or you ask all of them, because you can probe them well with a finite set. Did that answer your question?
Maybe I'll ask you after.
Okay, sure. Okay, so once again, so I want to kind of sum up where we are. What we want is we want approximate ergodicity with respect to volume. What we have is that for typical theta, you're actually ergodic, so this is going to 0. So what's the missing step? We want these two measures. Lambda theta, by the way, is the area on the invariant surface S sub theta. So we want that for rational, we want to be able to get close to the volume with respect to this invariant area, this area on the invariant surface. And so long as your group of reflections contains a small rotation, you will have this automatically. And this is pretty straightforward to see because our world right now is one-Lipschitz functions on the unit tangent bundle. And if you probe your set of directions pretty well, say by a small rotation, because you have a small rotation in your group of reflections, then you will have that your area measure is close to the volume. And so this will give you this, maybe with a 2 epsilon in place.
So this gives the Baire category examples of this type. What is expected if you ask for some measure theoretic typical?
I mean, I'm being recorded, so I feel afraid to say this, but nevertheless, I'll say it anyways. I would say that it should still be typically ergodic with respect to measure. This is way, I think it's way beyond what we have right now. Did that answer your question?
Yeah, you said. I asked you what's expected. You gave me your answer.
Yeah. Who knows what other people think, you know?
I'm sure they expect.
So at this, so Kerckhoff, Masur, Smillie give you what you want with respect to area, but oftentimes area is close to volume. And so then you can invoke the Baire category theorem, which is you fix thresholds for approximate ergodicity for 1 over n for each n of the naturals. You intersect over those, you get that what you're left with is actually ergodic. You worry that it's an empty set, but no, the Baire category theorem tells you that there's a ton of stuff in there. That's how the proof goes. I have more time than I thought. Great. So any questions on this proof? It's a nice proof, I think. Not due to us.
So you have no control over these open sets that you're intersecting? Or is that strong too?
Oh no, this is a fantastic thing. Thank you so much for this question. There's a beautiful result of Vordatz, who effectivizes this argument. And he says that if you are approximated by rationals at a rate of a 2 to the 2 to the 2. Yes, I think I have the right number of 2s. I could be missing one, but I think it's 3 in the exponent and then the genus, then you're guaranteed. So you can actually write
This
down.
is like Liouville numbers in sort of amongst the rationals.
Yes, yeah. It's a very strongly Liouvillean condition, but you can just write down a polygon and know the flow is ergodic. And this is due to Vordatz. Yeah, thank you so much for the question. I really like this result.
I'd be impressed if that was sharp.
Yeah. Okay, so me and Forney follow the same argument once we have our main theorem, which is the first one to obtain the weak mixing of a billiard in an irrational polygon with respect to the volume on the unit tangent bundle. we just replace Lipschitz functions on the on one copy with Lipschitz functions on two copies. Okay, approximate ergodicity of the product flows is the same. It doesn't really see this particular system. We replace Kerckhoff, Masur, Smillie's result by our result for products. And you obtain the density of approximations similarly, and the Baire category theorem applies as before. Any questions on this? Well, I have enough time for a couple of my questions before you guys get to ask your questions. So very much motivated by the question Jacob just asked, I would love to do this, to be able to tell you a specific irrational polygon with a billiard flow as weakly mixing. I am working on it with the two other people, Francisco and Giovanni. Let me just say our proofs need to be completely different. We apply to some measures rigidity results that seem way out of the realm of making effective. Now you could ask about rates of weak mixing. This has become a bit of a cottage industry, and I think it's a beautiful natural question. And you could ask that for billiards in polygons, but I think it's natural to sort of restrict your attention to certain classes. Why not regular polygons? And then you start thinking for a moment and you realize that the square and the hexagon are in the class where I ruled out weak mixing before in my work with Giovanni and Francisco. And so you ask for the other ones, whether you can prove explicit rates of weak mixing for the typical invariant surface. So in all regular polygons other than the square and the hexagon, where you're not even weakly mixing in your invariant surfaces. Okay. You can ask some other dynamical questions in regular polygons. You can ask whether there's a sequence of times where your dynamics raised to those powers converge, say, an L1 topology to the identity function f of x equals x. Or in this case, f of x comma theta equals x comma theta. And I would guess this is not true, but I don't know how to do it. I think it's hard. And there's this notion in ergodic theory called mildly mixing, which means no rigid factors. And so you could ask for a strong negation of this, which would be to prove that it's mildly mixing in the typical direction. And for these kinds of things, this is sort of the highest amount of chaos you could hope for. They can't be mixing by a theorem of Katot from about 1980. So mild mixing would be the most you could hope for, whatever that means. And then you could ask about the exceptions to these sets. For technical reasons, sort of things with that are, so there's many equivalent definitions of weak mixing. One of them is that you have a non-constant eigenfunction. And those come in two flavors. They come those that exist for very good reasons, and those are the continuous ones. Asking to control those seems, I don't know how to do it. I don't even know how to begin starting to try to do that. So let's ask for the ones that are not continuous. And then you could ask for hopefully genus independent bounds on their Hausdorff dimension, on their size. So we know almost everyone doesn't, but can we say something about their size? Yeah. And you can ask for upgrade of ergodicity called unique ergodicity. Thank you for your time.
Are there any questions?
This mixing is not possible.
In the rational case, in the irrational case, it could be. It seems very, very hard. Sorry for interrupting.
Yeah, okay, no, I didn't remember. Is there a notion of, is it a natural notion to look in 6, 7 definition equivalences where you might take not product of 2, but product of more. So kind of 3 mixing, 4 mixing. That makes sense. And
weak mixing, because ergodicity, because weak mixing means product ergodicity with any transformation, you get that if you took 7 products of your transformation with yourself, you'd also be ergodic for weak mixing. So it's sort of the formal version where you ask for multiple, it follows immediately from the one of the definitions. Did that answer your question?
Yeah, yeah.
I think this mild mixing in the case of regular polygons is sort of a natural thing. the natural sort of next step to shoot for.
What's known about unique ergodicity, you said?
Oh, yeah, Kerckhoff, Masur, Smillie proved that for every translation surface, for almost every direction, the flow is uniquely ergodic. You could now ask about the product of flows in different directions. And Pascal, who Baire and me proved that this is true for almost every translation surface with respect to every SL2R ergodic measure. Also, Claire Brouin and Sam Fairchild proved that this is true for billiards and regular polygons, other than the square and the hexagon. The square and the hexagon, it's easier to see. They did the hard version. So it's true for billiards and regular polygons. Did that answer? Yeah.
I'm just curious, to what extent does this result depend on the speed of the flow? So if I give you a continuous function of your polygon and I have your flow speed up at various parts according to the function, would it affect the mixing results?
So these results tend to be very sensitive to perturbation, mixing and weak mixing property. Ergodicity isn't, it doesn't sort of care about these perturbations. These properties care a lot. It's not that surprising if you kind of stare at a eigenfunction equation. You could say, well, if I mess up the flow, I'll mess everything up. And it tends to be that the lack of weak mixing is easy to break. Now, your particular question I haven't thought about, so I'm just putting it sort of into a little bit of context. Thanks for the question. I hope I answered it. Yes.
Yeah, so I think somehow what's a little bit disturbing about the there exists a polygon statement is it's in contrast with the elementary nature of the problem that you began with.
I agree.
What does it look like?
I agree. That's why I think it's an interesting question worth doing, you know? I agree 100%, yeah.
I mean, do I have a bound on the size of the polygon? Like, you know.
Oh, it's scale independent, right? If it's true for a polygon, it'll be true for its dialing. And all of these are about any number of
do I have a
sides.
bound on the number of sides of the polygon?
Yeah, it'll be true for triangles, 4 or 5, it sort of doesn't see. It's sort of a more combinatorial thing. You fix your combinatorics and then it's typical in that class. And also going back to your question about billiards in that are not convex, you could imagine I let you have a pair of 4-sided objects, one on the inside and one on the outside, and I move in between them for the typical configuration like this in the sense of the Baire category, so a G delta dense set of these side choices. Of course, I can't help myself, but I draw a square without trying. Oh, if you let yourself vary the angles and the sides, you'll get something that's typically ergodic with respect to volume on the tangent bundle. That answer your question and connect back to your earlier question.
Yes, but I have another question.
Yeah.
What happens if you go to a higher dimension? So suppose
Oh gosh.
I
go home.
I
I run home screaming. Yeah, I don't know. I think Euclidean solids, it's like just supernatural. And this cube we know, I just think it's supernatural. I hope I'm not at all coming off as demeaning your question. I just don't know. I think it's a fantastic question. Really, it's fantastic. Yeah.
I have another question. So those translation surfaces, you can think of them as being just a billion differentials on common surfaces. So your conditions that you don't have an affine map to S1. I guess this is just a condition on the hard structures that you get on the 2 plane corresponding to the differential, or?
Yeah, so the version we actually use, in order to work with this, it has a very good notion to work with, which is that you have a non-trivial integer vector of cohomology, which intersects the tautological space.
Okay, so.
And that's really a workable. Yeah, and that's a really workable good condition, and that's what we really use.
Okay.
Thanks for the question.
Goodkin, is it Goodkin? He conjectured something along this.
Yeah, so we answered.
How did he come by?
What?
How did he get that condition?
I am not sure he counted this condition. I'm not sure. He uses 2 different versions of approximately integrable. I'm not 100% sure. Kind of this. Yeah. I don't know. It's the perfect answer.
Any other questions? My personal.